So it is not just a proof for why the square root of 2 is irrational, it is also a proof for why the nth root of any prime is irrational. Isn't that incredible? I'm really happy. I'm really happy. Hi everyone, greetings from Colombia. I am Sharif Velásquez and welcome to the best channel in the world, Always Curious. Of course, that fact is verified by me, so you do not need to look that up on Google. Today's video starts with a short story. I used to have a teacher that in one class he showed us the proof of why the square root of 2 is irrational, the usual one. And then he said, memorize this proof because this is going to be part of the exam. For 2 weeks, the class would go like that. The teacher would do the demonstration and he would make sure that we all memorized it. I have to be sincere with you. I really disagree with this teaching method because it kills the essence of mathematics. Mathematics is not about memorizing. It is about creating things, discovering things. It is about imagination. And so I decided to tell my teacher I disagreed. And also, the day of the exam, I tried to protest against that in a very peculiar way. I tried to discover or invent, depends on the point of view you have of mathematics, a new proof for why the square root of 2 is irrational on the spot. So during 1 hour I was trying to find a new demonstration for why the square root of 2 is irrational, and eventually I found one. And so I wrote it down and I gave the teacher my exam. 1 week later he gave us all the exams except for me. He said, Velásquez, I'm still reviewing your exam. Come to my office tomorrow. And well, when I arrived to his office, he said, congratulations, that proof was really good, but you have one error. And he showed me the error. But I left that office really happy because the teacher saw my proof. I thought he was going to say, hey, that looks pretty good. Yeah. But he took his time and I was really happy. And so I was also really proud of the proof. And I corrected all its logical errors. I think maybe there's a logical error here and there, and I have noticed. And that's the proof that I am going to show you today. Now, when I say a new proof, take that with a grain of salt, because maybe someone has already discovered this proof. But I searched on Google proofs for why the square root of 2 is irrational, and I didn't find something like that, something similar. So I like to think that it is a new proof. Yeah. But yeah, take that with a grain of salt. So this is my board, and let's begin with demonstration. Goodbye. Hi everyone, here I am again with my board. In a few seconds you're going to be looking at some footage of the setup I have for all this video. And as you can see, this board is risking its life. It can fall at any given moment, and the same goes for the camera. So, yeah, I mean, my savings are at risk because I bought this board just so I could make all these YouTube videos with my savings of last year. So yeah, let's just begin with the proof itself. First of all, I have to say that this proof uses not advanced mathematics, not really advanced, but mathematics that are a bit higher than those we see in high school. So you just have to be comfortable with mathematical proofs. That's the only thing you need, and with logical statements. That's it. So yeah, let's begin now with the proof. So we're going to start by doing what a usual proof for the irrationality of the square root of 2 does. So let's assume that the nth root of 2 is rational. Let's assume that. For every n greater or equal to 2 with n belonging to the natural numbers. Yeah, that's the first thing. Now, if this is true, then we can say let a comma b be two natural numbers. Yeah, we are going to see why natural numbers, such that instead of integers, such that the square root of 2 is equal to a over b. This is literally the definition of a rational number. This is equivalent to saying that when we raise both sides to the power of n, to say that a over b to the power of n, and this is equivalent to say that 2 is equal to a to the n over b to the n to the power of n. And that's the first thing we have to do. Here it is, our first step. Let's call this equation as equation 1. Okay? Now, why did I assume that a comma b are two natural numbers and not two integers? Well, because we can do the test. There are 4 cases. No? A is a positive number and b is a positive number. A is a negative number and b is a negative number. A is a positive number and b is a negative number. And a is a negative number and b is a positive number. Yeah? Those are the 4 cases. In this first case, a over b will be equal to some positive number. In this other case, a over b will be equal to a positive number. In this case, a over b will be a negative number, and in this other case, a over b will be equal to a negative number. Okay? We know that the square root of 2 is not a negative number. So, these cases cannot be true. We are left with this 2. Okay? And since they are equivalent, yeah, we can just assume the first one, for example. Yeah? And it is going to be exactly the same. Because if a were to be negative and b were to be negative, we could just extract -1 as a common factor, and then this would become a positive, well, both would become positive. Yeah? So, for the sake of this proof, we have to assume that a and b are positive, and therefore they belong to the natural numbers instead of the integers. For this second part of the proof, we are going to use the thing that is different from the usual proofs, and the idea I had. The omega function! So, why omega function? Well, because I think that the omega letter of the Greek alphabet is really beautiful. So, the omega function. Now, what does the omega function do? Let's see. First, we're going to see a very intuitive definition, not a mathematical one. So, let's see. If we have two numbers, x comma y, two natural numbers, yeah, such that both of them are greater than 1, or let's say greater or equal to 2, or I don't know, greater than 1, yeah, we can define the omega function as, let's say, the omega function of x comma y will return the number of times the factor y repeats in x. Okay? I'm not really good at making intuitive definitions with words, so I'm going to show you some examples here. The omega function of 4 and 2 will be equal to 2. Why? Because when you decompose the number 4, you are left with 4 is equal to 2 times 2. You can see 1 and 2. The 2 repeats 2 times in 4. The omega function of 8, 4 will be equal to 1. Why? Because when you decompose the number 8, you are left with 2 times 2 times 2, but this is also equal to 4 times 2. Yeah? And as you can see, the factor 4 repeats only one time. 1. Let's test and let's have another example. Omega function of 3, 2. That's going to be 0. Why? Because if you decompose number 3 times 1, then the factor 2 is not going to be present. So there are no 2's. Doesn't matter how you arrange the prime factors that compose 3. And the last example, let's say 20 and I don't know, let's say 2. Yeah? How many times? Well, let's see. 20 is equal to 2 times 2 times 5. So this would be equal to 2. If this were to be, let's say, a 5, then this result would be equal to 1. If this were to be a 10, then the result would be also 1, because 5 times 2 is equal to 10. I think you get the idea. I mean, it's kind of intuitive definition of the omega function. But in mathematics, we cannot work with intuitive definitions or definitions that are created with words. So let's define the omega function in a mathematical way. That sounds very weird. And how are you going to define it mathematically? Well, you are going to see. So let's see. As we saw earlier, this intuitive definition using words is not enough. We have to find a mathematical definition for the omega function just so we can use it. But before that, I would like to say two things. The first one is that I am not going to write down everything I say, because this is not a paper where everything has to be written down. This is an explanatory video. And the second thing is that sometimes you'll see me looking up. That's because I have some notes there. Because I cannot memorize all the mathematical facts and steps we're going to follow. So yeah, let's now begin with our mathematical definition of the omega function. We're going to use the fact that for the omega function of x, y, we can express x like this. X will be equal to y to the power of z times some q, where z is a natural number or 0, and q is a natural number. Now, here I assume that the natural numbers do not contain 0. That's a big fight of mathematics. But yeah, just have that in mind. And the second thing is that I'm going to say z instead of z. That's because z and c are really confusing. And we are going to use the letter c later in the proof. So, yeah. Now, as it is not really difficult to notice something. That z represents the number of times the factor y repeats in x. So z is the thing we are looking for. Z is our definition of our omega function. So let's solve for z. Okay? We have this x is equal to y to the power of z times q. This is equivalent to x over q, which is equal to y to the power of z. And this is equivalent, if we apply log y in both sides, this is equivalent to the value of z. But there is a problem. Z doesn't have one value. It may have 1, 2, 3, 4, 5 infinite values. Why? Because let's take, for example, the omega function of 8 and 4. We can express 8 like 4 to the power of 0 times 8. But we can also express 8 like 4 to the power of 1 times 2. Which of these is correct? Well, both are correct, the equations. So, but what is the one that defines the omega function? Well, the one that has the biggest value for z. So, we have to say that in order for z to be equal to the omega function of x comma y, we have to say that z is the biggest integer value for this equation, or the biggest natural integer value. So, z is the biggest natural integer value that satisfies the equation log y of x over q equal to z, where q is the smallest natural integer value such that log y x over q is a natural number. Take your time. Because, I mean, you can find z as the biggest natural number that satisfies this equation. And for doing that, you can also say that q is the smallest natural number that satisfies this equation. Yeah? Such that this value is the biggest natural number. I don't know if you understand me. I'm really bad at this with using words. Oh, wait. My father and my brother arrived. So, wait a minute. I'll be back in a few seconds.
Y eso. Ah, bueno. El rollo solucionar.
Sí, pues. Bueno. Hola. Soy mi papá y mi hermano. Put away less sad. I may be wrong. I may be wrong. Okay. So, no. You saw my brother and my father. So, yeah. Now, now that we have this definition, yeah, we can say then that if z meets these conditions, then z is equal to the omega function of x comma y, which in other words means that the omega function of x comma y is equal to the log y of x over q. Yes? With q being the smallest natural integer such that this thing is a natural integer. So yeah, we have a mathematical definition for our omega function. Now that we have a mathematical definition, sorry, not a mathematical function, a mathematical definition for our omega function, yeah, I am going to show you a property of this omega function. And this property will allow us to prove that the square root of 2 is irrational. So, pay attention. If y is a prime number, then the omega function of x to the power of c will be equal to c times the omega function of x comma y. Wow! So this property, we can come up with the idea of this property because it is really kind of intuitive. Take, for example, the omega function of 100 and comma 10. Yeah, we can express 100 as 10 times 10. Okay. Now, if we raise 100 to the power of 3, this group of factors repeats itself 3 times. 10 times 10 times 10 times 10 times 10 times 10. So it is pretty intuitive to say that if this repeats it 2 times, this 10 factor repeats itself 2 times in 100. If we raise it to the power of 3, then it is going to repeat 6 times. Yeah? Why does y have to be a prime? Well, we're going to see that in a few moments. And because I didn't point out that y was a prime, my proof was wrong. Yeah, my proof was wrong because of that. So let's see. Let's find the proof for this property. Proof of this property. I really don't have any for this property, so I'm gonna call it property number 1. So if you have a really cool name for this property, leave it down in the comments. I'm gonna pick the best name for the property. So yeah, let's begin with the proof. Proof for property 1. Let z be equal to the omega function of x comma y, and f be the omega function of x to the power of z comma y. Now, because of our mathematical definition of the omega function, we can say that z is equal to the log y of x over q. Well, where q is the smallest integer, yeah, and we can do the same for f. F is equal to the log y of x to the power of c over w, not q, w, because they are 2 different numbers. And the same goes for okay, yeah. Now that we have this definition, we can solve for x and x to the power of c in both equations. More fast forward. Times W. Yeah? Now that we have this, we are going to assume something. Yeah? If y is a prime, yeah, we can conclude that y does not divide q and that y does not divide w. Why are we going to do this? Well, this is going to be useful in the future. You'll just trust me. But why do we say that if y is a prime, then this is true? Hi, I am Sharif's twin brother, and he has me in the basement. I have to edit all his videos, and while I was editing this one, I noticed that the camera stopped recording. So I'm going to show you the answer, or kind of the answer, for why y has to be a prime. That is something you may be asking. Take this counterexample. 8. We can express 8 as 4 times 2. Let's say we want to raise 8 to the power of 2. I don't know. This would be 4 times 4 times 2 times 2. Yeah? The omega function of 8, 4 would be 1. And the omega function of 8 squared, 4 would, according to this property, be 2. But no, that's not true. It would be 3. 1, 2, 3. So, when y is not a prime, we cannot guarantee that it doesn't divide q. And that is a really big problem. When y is a prime, we can guarantee that y cannot divide q, but that would be left as an exercise to the viewer. So, bye. So now that we have this, we can replace x in the value of f. Yeah, or x in x to the power of c. I mean, let's just call this first equation asterisk, and this one double asterisk. Now, we can replace x in the double asterisk equation. So, this is going to be like this. Y to the power of z times q to the power of c is equal to y to the power of f times w. As you can see, this here can be is equivalent to saying this. W. We want to show that z times c is equal to f, because with that we would complete our proof. But we cannot do that yet. Why? Because we have to argue that z times c is the greatest value that the exponent of y can have for the case of x to the power of c. I don't know if I explain myself in the best way, but yeah, let's just prove it. Now, we can do this. We can say that y to the power of z times c over y to the power of f is equal to w over q to the power of c. Let's write this down. So let's erase everything. Let's erase all of this. And now we have that y to the power of z times c over y to the power of f is equal to w over q to the power of c. Now, this is also equivalent to saying y to the power of z times c minus f is equal to w over q to the power of c. There are three cases. Yeah? Case 1, let me write this down again. Z times c minus f is equal to w over q to the power of c. The case 1, z times c minus f is greater than 0. Case 2, z times c minus f is equal to 0, which means z times c is equal to f. And the third case, sorry, I'm blocking your view, minus f is lower than 0. Yeah? Let's evaluate case 1. If this case 1 were to be true, yeah, that would mean the following. We have this, minus f is equal to w over q to the c. We can multiply both sides by q to the c, and we are now left with this. And if this is greater than 0, this means, this would imply that w is divisible by y. I don't know if you see y. Good joke there. Well, I mean, so this would imply that w is divisible by y. Yeah. So therefore, we can conclude y divides w. But we already said that if y is a prime, y does not divide w. And this is a contradiction. Case 1 is impossible. Let's evaluate case 3, not case 2. Case 3. It is more of the same. It's exactly the same thing. Because y z times c minus f is negative, yeah, then we can just elevate, raise everything to the power of minus 1, and we're left with this. F minus z times c is equal to q to the power of c over w. And so, we can do the same thing. Y to the power of f minus z times c times w is equal to q to the power of c. Yeah? And we already said, this implies that since these is not equal to 0, yeah, that this value is positive, this implies that y divides q to the power of c. But we already saw that y does not divide q to the power of c. This is a contradiction. And therefore, case 3 is not possible. Then we are left with case 2, which is evidently true, because these two cases are impossible. But let's just show why. We could say this. Why? Let's just make some barriers here. No, you cannot cross this side, and then you can go that. Yeah. Y to the power of z times c minus f times q to the c equal w. If these two are 0, then this would mean that q to the c is equal to w, there is no contradiction. Yeah, and so case 2 is the only case that is true. Let's erase all of this. Now, because of this, we can conclude that z times c minus f is equal to 0. But if this is true, then this is equivalent to saying that z times c is equal to f. We did it! Yeah, we did it! And now we can also conclude that y to the power of z times c minus f being equal to w over qc leads to the fact that y to the power of 0 is just 1, so 1 times q to the power of c equals w, and this is the same as saying q to the power of c equals w. Remember this, and also remember this. Yeah? Now, because of all of these steps, we can now conclude that, let me erase all of this. Let me also erase all of this. As we said earlier, f is equal to the log y of x to the power of c over w. But what is f? F is the omega function of x to the power of c comma y. We can also say that since w is equal to q to the power of c, we can replace w with q to the power of c. Log y x to the power of c over q to the power of c. We can just extract this power and we're left with this log y x over q to the power of c. This is equivalent to saying that the omega function of x to the power of c comma y is equal to, because of the properties of logarithms, c times log y of x over q. And because and now as we can see, log y of x over q is the same as z, but z was equal to the omega function of x comma y, and therefore the omega function of x to the power of c comma y is equal to c times the omega function of x comma y. Epic! This is just epic! Now, this is the proof for property 1. Okay, now we are reaching the final steps. Basically, this is the last step of the proof. As we can see, we saw earlier that for the nth root of 2 to be rational, this would have to be true. B to the n. But if this is true, then this is also true. Sorry, b to the n, no. 2 minus the omega function of b to the n comma 2 is equal to 1. This is really not so hard to see. This is very, very, very intuitive. This is going to be left as an exercise to the viewer. The video would be very, very large if it is not already very long video. But as you can see, let's say a to the n is equal to 2 times 2 times times determine w, and then b to the n is equal to 2 times a determined j. Yeah, then all the things would cancel out. This 2 would cancel with that. For this division to be true, then 2 should be the only factor left in A over n after the division, and therefore the number of times the 2 repeats as a factor in b to the power of n has to be 1 less than the number of times the 2 repeats as a factor in a to the power of n. These 2 are not equivalent, but this one leads to this one. Okay? So, yeah, as I said before, this is going to be left as an exercise to the viewer. Now, we can use this fact to show the following. Yeah? Because of our property number 1, we can say that the omega function of a to the n comma 2 minus the omega function of b to the n comma 2 is equal to 1. We know that a to the power of n is a natural number. We know that 2 is a prime, and we know that b to the n is a natural number. All the conditions are met, and therefore we can say this: n times the omega function of a comma 2 minus n times the omega function of b comma 2. This is going to be equal to 1. Now we can extract n as a common factor, omega of a comma 2 minus omega of b comma 2. And we are done. Why? Because the omega function of a comma 2 minus the omega function of b comma 2 will be equal to 1 over n. This is a contradiction. Yeah. If you cannot see why this is a contradiction, well, let me show you this. We know that the omega function of a comma 2 is an integer. And we know that the omega function of b comma 2 is an integer. And we know, yeah, that when we subtract these two, the difference between them is also a natural number, because it is greater than 0. It is greater than 0, and therefore this has to be a natural number. So, yeah, all of this is a natural number. We know that n is a natural number, and it is greater or equal to 2. And therefore, 1 over n is not a natural number. This is a rational number. And basically, this is a rational number that does not belong to the natural numbers, no matter the value of n, if n is greater or equal to 2, as we said before. And therefore, 1 over n does not belong to the natural numbers. But since these two are equal, we can say that 1 over n, belongs to the natural numbers. So we have that 1 over n belongs to the natural numbers, and that 1 over n does not belong to the natural numbers. This is a contradiction. Contradiction! And therefore, our initial assumption has to be false. This means that if we assumed that our assumption was assume that the nth root of 2 is a rational number for any n greater or equal to 2 with n belonging to the natural numbers. Okay? And this is false. Our assumption is false. Which means that the nth root of 2 is irrational. And since n is greater or equal to 2, if we make n equal to 2, we have shown that the square root of 2 is irrational. That was epic. That was an epic demonstration, and well, if you reached this part of the video, thanks a lot for your dedication. This is my first video, so I am really not used to making videos, and therefore this one may seem really long video. Sorry for that. But yeah, now you know a new proof for why the square root of 2 is irrational. Guys, I mean, I was just thinking about it, and I just finished the video. But now that I think about it, this proof is not just for showing that the square root of 2 is irrational. With this proof, we can prove that the nth root of any prime number is irrational, because the property number 1 of the omega function is true for if y is a prime. So I mean, we can use the same logical reasoning to demonstrate that for every prime. So it is not just a proof for why the square root of 2 is irrational, it is also a proof for why the nth root of any prime is irrational. Isn't that incredible? I'm really happy. I'm really happy. So yeah, just wanted to point that out. Bye. Thank you all for sticking around if you're still looking at this video. I really have to say thank you. Thank you for paying attention and looking at a very large video. And yeah, just wanted to say subscribe to the channel if you like this kind of content. Tell me what you think about it in the comments below. Look the other videos I have in the channel if I have any other videos. And you can follow my other channel, Always Curious in Español, because, well, my native language is Spanish, and so I upload the same videos you see here. I upload them but in Spanish. So if you're learning Spanish or you speak Spanish, go there. Yeah. Also, I wanted to tell you that in my personal channel, Sharif Velásquez, literally the name of the channel, I upload videos related to me, but I'm planning to upload ukulele tutorials and some piano tutorials too. So go there and pay a visit. Thank you and goodbye.